Hey gang, and welcome back to another Worksheet Solutions walkthrough for the worksheet, Alkyne Reactions and Keto-Enol Tautomerism. If you're new around these parts, Worksheet Solutions walkthroughs go a little bit like this. You've seen an instructional video on jOeCHEM, or maybe you went straight to the worksheet for some good old-fashioned practice. Maybe there's a problem, two or more, that you're looking for an explanation for. Or if you're here because of that reason, you're in the right place. We're going to step through this worksheet, we're going to go problem by problem, and hopefully along the way you'll get the explanation you were looking for. So let's go. In this first part of the video, we're going to look at the first 5 problems, complete the reaction section. So problem 1, page 1, let's go. Alright, so if we take a look up here, right, we're just going to take it one step at a time, like we always do. So you can see right here we have 2-butene, just a regular old alkene. And then in this first step, right, we're going to do some work on the side, right, like we always do, take it one step at a time, getting to that final product. So with this 2-butene, this is an alkene reaction. We're going to put bromine across the double bond, right? We don't have any active solvent. It's just CCl4. It's just a solvent. It's not going to participate. So if we're going to have a little one in the margin, the very first thing is we're going to have a bromine and a bromine just across the double bond. And hopefully you see one in step 2, we just have 2 equivalents of sodamide, right? So this is where the alkene chemistry comes in. We're just going to do a double elimination for the bromines right here. So NH2 minus is going to do an E2 for this, and kick off this bromine. We'll have a double bond, and then a second time right there for this bromine, that will form a triple bond for us. So really we have 4 carbons, and in between where there was a double bond, now there's a triple bond. So make sure, right, we are not doing stuff like this, because this does not reflect the linear geometry of alkynes. Remember, there needs to be a 180-degree bond angle between the carbons, and remember, that's a carbon and that is a carbon. So don't get confused, don't lose points for not drawing things correctly, because we work so hard for these points. So don't let anyone, any points get away from you. Okay, so in problem 2, I hope what you're seeing is, so we have an alkyne right here. We know that these hydrogens are a little bit more acidic because of the sp hybridization of these alkyne carbons. So in this first step, we're just doing an acid-base reaction, right? LDA is just going to deprotonate, and we will form an alkyne nucleophile, which we will then use to do SN2 in this second step. We are just going to attack that carbon. We will kick off bromine. So this product will look like we still have the 2 carbons in our original acetylene reactant, right? The common name for ethyne, acetylene. And we just have this extra CH3 tacked on. So this works, or this works. If you want to explicitly write CH3, up to you. Okay? Now, next 3 reactions, we have the same reactant, so let's see what we're working with here. So, I hope what you're seeing is we have H2PDC, and we have 2 equivalents. So really, this reaction is just forcing hydrogen across this triple bond. We're going to take it from a triple bond and hydrogenate it back to a single bond, okay? So we're forcing hydrogen across these carbons right here 2 times. So we have 1, 2, 3, 4, 5 carbons. We're just going to end up with regular old straight chain pentane, okay? Now, in this reaction, we have a little bit of a different thing going on. We don't have just a regular H2PDC. We have liquid ammonia and elemental sodium, and these are hydrogenation conditions that will take this triple bond down to a double bond, but not just a double bond, right? We will have a trans double bond left over, okay? So 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. And our double bond is on carbon 3 and 4. So 1, 2, 3. And you can see I've drawn the trans double bond because when we trace over the double bond, we cross the double bond, okay? Now, down here, unlike the reaction above, this is going to be a hydrogenation, but not to make a trans double bond. We are making a cis double bond here, okay? So again, we are working with 5 carbons. Our double bond is between carbon 3 and 4. So I'm going to draw, this 5 carbon chain, but it needs to look different. It needs to be a cis double bond. So 1, 2, 3, and I'm going to draw my carbon 3 and 4 like this, so you can see 1, 2, 3, 4, and 5. And I drew it like this because if I draw my dotted line right there, you can see in tracing over the double bond, I don't cross that dotted line. So therefore, this is a cis double bond, okay? Gang, that does it for the first page. Let's chug on to the second page. Moving on to page 2, we have 5 of the remaining 6 complete the reaction problems for problem 1. So, in taking a look up top, I hope what you're seeing is something that's not scary, something that we already knew how to do before we even started talking about alkynes. So if we take a look up here, we have 2 equivalents, right? 2 doses of HCl for this alkyne. So all we really need to do is that all that Markovnikov addition, train of thought applies directly. We are going to protonate this triple bond, form a carbocation, Cl attacks, and then guess what? We do it again. So I think we can all agree that first and foremost, we'll make a carbocation that looks like this, and then Cl attacks. So after the first protonation and attack, we look like this, and we do it again. So we will protonate the double bond, which will then become a single bond. We will have a carbocation in that secondary position. The second Cl minus from the second equivalent of HCl comes in and attacks. So when we get a product over here, really you just do a Markovnikov addition 2 times. You get a chlorine on the carbon that is your most stable carbocation. This happens to be the secondary carbon in this structure, which is propyne. We then have a dichloride structure over there. Bonus points, this is you could say this is these chlorines are geminal to each other because they are on the same carbon, okay? So, moving on to this question right here. So, when you see this, just also know that you could very well, in place of the H2O and H+, you could have something like H2SO4. Basically, if you see mercuric sulfate and some acidic conditions at all, right? What you have is you're going to hydrate this triple bond. You will add water to it. It will then flip, it will then be an enol, and it will flip to a ketone. So this is just a Markovnikov addition of water. So we will be working with this carbon right here. And just know you don't end up with an alcohol. You end up with a ketone. You end up with a carbonyl, right? So we're dealing with ketones or aldehydes. Here it's a ketone. So our product looks like this. The benzene ring was just decoration. So nothing happening at this carbon, so we have 2 more carbons. So that was 1, 2, 3, ketone right there. Okay, so now same structure but different reagents. This is the same exact thing. This is an addition of water to a triple bond. However, right, we will still go through that, enol intermediate. We will flip to the carbonyl. But here we're going to do an anti-addition, right? So instead of adding the initial OH to this carbon, we're going to do it on the least substituted carbon that is a part of the triple bond. So, unlike the structure right above it, we don't get a ketone, we get an aldehyde. Our structure looks like that, okay? So, again, same idea, I just kind of want to really reinforce it, bring it home. So we will be adding a carbonyl to this carbon right here, the terminal carbon. 1, 2, 3, 4 carbons. 1, 2, 3, 4. End up with an aldehyde right there. And then 1, 2, 3, 4. So next structure. So same reactant, different reagents. We're doing the straight up addition this time. 1, 2, 3, 4. We will be working with this carbon right there. 1, 2, 3, 4. We end up with a ketone on carbon. Well, it's the second carbon, really. Okay, gang, that almost does it for page 2. I didn't have room for the 6th and final problem, so let's tackle that real quickly. Then we have some more challenging problems. I think you're going to like those, so we'll just keep having some fun. Okay, gang, to finish out problem 1 and finish page 2, we have this lovely, super, ridiculously long complete the reaction problem. But we are unfazed, we are calm, and we will take each reaction step one at a time. So we have lovely ethane. So first and foremost, I'm going to do my work over here. This is nice because we're only doing just this one. I did this on purpose. So free radical bromination on ethane. Going back to our roots, all we're going to be doing is putting a bromine on either side. You know, your pick, it's the same. So this is what we'll have after the first step, 2 carbons and just the bromine. Now with step 2, LDA, giant bulky base. Yes, I know this is a primary carbon, but we have a good leaving group. There's no chance in hell LDA is doing SN2. This is our surefire, you know, method to do elimination, E2. So we go ahead and I'll draw this real quick. Pick off the neighboring hydrogen, drop the electrons down, boot bromine, we get ethene. Step 3, looks like we are going back to alkene world. We have Br2 and carbon tetrachloride, just a non-participating solvent. We will shove 2 bromines across this double bond. Okay, that's step 3. Step 4 is a double dose of Sodomid, right? This is our method from taking a structure with good leaving groups adjacent to one another and doing a double elimination. This will give us an alkyne, right? So now we're leaning on chemistry we've recently learned. So now, that was 4. Okay, so 5, right? We know sp carbons have that more acidic nature to that, you know, any protons they have. So what's going to happen here is LDA will just deprotonate that, and we will generate, I'm going to do this actually, and put this over here. We will have a terminal alkyne nucleophile, right? So we're just, you know, step 5, we're just going to rip this proton off from LDA. Electrons get dumped onto this carbon. That is now a nucleophilic carbon rearing to attack something, SN2, do anything. And sure enough, in 6, we are, you know, delivered to it is formaldehyde, right? So let me go ahead and even, I'll draw it up here. We have lovely formaldehyde, and our acetylene nucleophile will attack, electrons will kick up. So in 6, we have this. So this carbon right here that I will dot is this carbon right here. So I need to go ahead and draw the fact that we have an O minus. Okay, and last but not least, just some workup, protonate that sucker, OH. So our final product is a 3-carbon structure. We have the triple bond, and we have an alcohol as a result. Okay, gang, I wanted this section, maybe not, this problem was long, but I wanted this to just be repetition. Get used to these new alkyne reactions. These next problems, I wanted them to be harder. So let's get after them. If they were a little confusing, if that's maybe why you're here, don't worry. They were supposed to be hard. Let's jump on to the next page. Okay, gang, now we charge on to problem 2. And the way I want to tackle these next 4 problems is to do 2 here, you know, have more room to draw on the board for me so I can show you more, and then tackle the next 2, and then we'll head on to the last problem. Okay, so in looking at this first problem, we see we have an alkyne, we have a triple bond in our as our reactant, and we're just going to take this one step at a time, you know, to get through the end of the reaction. So you can see in the first step, we're going to H2 and Lindlar's this triple bond and take it down to a double bond. So I'm just going to go ahead and start working right here. So in particular, this is going to be a cis double bond. We'll see if that character sticks around. But 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so that's step 1. And then I'll draw a line. And you can see in step 2, we're actually going to take that double bond and we're going to make an epoxide out of it. So at this point, you have 2 options. The epoxide will be formed across this double bond on the same side, right? It's going to be a syn addition. So the way I'm going to go about this is I'm going to go ahead and draw these 2 carbons right here. And I'm going to choose to wedge my epoxide, okay? And one other thing is that we have 2 hydrogens over here. So what I'm going to go ahead and do is, because we have this cis double bond right here, I'm going to reflect that the alkyl pieces be on the same side and the hydrogens be on the same side. So what I'm going to do is I'm going to keep these as flat line components, which means we will have hydrogens as our dashed components, right? So you could have totally done the exact same thing, but made the, you know, any different combination, but as long as these components are kind of like on the same side, ish as the, you know, where they are, you know, it's like the hydrogen's not where the methyl is and whatnot, you should be okay. We will probably have a racemic mixture come out of this because right? We could have very easily made the epoxide with 2 dashes, so keep that in mind. So moving on to step 3, and I'm not going to draw a line here because step 3 is to toss in an alkyne nucleophile, right? So because this alkyne nucleophile is negative, well, I'll put this where it kind of belongs. Think of this as attacking an epoxide in basic conditions. We are looking to attack the more sterically available carbon, right? So between this isopropyl group off of this carbon and the methyl, we're definitely going to attack the carbon that is sporting the methyl group, okay? So this will come from the backside, which is going to be a dash. We will attack here, and then we will boot these electrons onto the oxygen up there, functioning as our leaving group. So let me draw this result over here, and then we can kind of get into what is going on, and I'm just going to start to naturally separate these problems, okay? So I'm going to keep my home base right here. I have my wedged O-. I then have my isopropyl group down here. I have this, I don't have to draw that hydrogen, but I'm going to. I have the dash going to the triple bond. So notice that is the carbon, that is the start of our triple bond. I still have the straight line, and that means, so because we are coming from the backside, right, we have to bond as a dash. Something has to flip up to be a wedge, and that will be this hydrogen. Okay? So, to prove to ourselves this was good and that we inverted stereochemistry because we did do attack, very quickly, if we look at this carbon right here, the highest priority group is the oxygen it's attached to, then it's going to be this piece over here, then finally the methyl. Our lowest priority group is facing away from us, so this particular carbon right here, it looks like S, and it actually is S. But if we do the same analysis over here, highest priority group is actually still this piece over here because we have a tie at the carbons, but this carbon's attached to an oxygen. Then we have the triple bond, and then we have the methyl. So while we look like S here, we are in fact R because our lowest priority group is facing towards us. So we inverted our stereochemistry, we took care of business. This is our final product. I'm going to leave this like this. And I did say assume workup, so I'm going to go ahead and erase this, tack this on. This is your final answer, and plus an enantiomer because of what we said when we formed the epoxide. So kind of a lot going on there with the attack and making sure you form the epoxide correctly and everything like that, but that's why I view it as a more challenging problem. Okay, let me just make sure I do that absolutely correctly. Yes, I did. Okay, cool. Moving on. So this problem, I kind of like this because there's a lot going on, and it's really that we need to fill in the blank. We need to fill in the reagents to make sure that this actually transforms into this. So I think a retrosynthetic approach here does help. So I hope what you're seeing, and we do see plus an enantiomer, okay? That will help us out. So if we take a look at this, hopefully you're seeing 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and then we have this extra ethyl piece and then an OD. So it's lame. It's always stupid when deuterium shows up, but I like to show it to all of you just so you're prepared for it when it does rear its ugly head. But what I'm thinking here is because we have a plus enantiomer, we must have attacked something that was sp2, right, trigonal planar and flat, because there was no preference to attack this way or this way, and this ethyl was the thing that attacked it. So I know this is kind of a lot to digest as a first step, but I hope what you're seeing is if we were to kind of step this back, maybe we attacked a carbonyl here, that would explain where the oxygen came from, and we attacked it with ethyl Grignard, okay? So I think what we did here was an ethyl Grignard attack, and the carbonyl we attacked, that got attacked, looked like this. Okay, just like that. Now, however, that's not all that we would have to include in this step. And don't worry, the numbering, we'll sort that out later. We could have attacked, but what's the workup? The workup's particular in this scenario because we have deuterium left over. So after the attack, we must have done there must have been D3O+, right? That's where the O- that would have resulted from this attack, it would have absolutely grabbed D+ from D3O+ being around, okay? So this gives us a lot to work with because now we just need to make this happen. We just need to take this double bond up to the carbonyl, and that we can do. Let me just make sure I remember how. Okay. So there's probably multiple ways you can do this. There's actually a very smart way to do this, and I'll show it to you. But the way I chose to do this, to keep in the spirit of alkynes, is if you step this back, if we used HgSO4 and H2SO4, you know, or just H+, whatever you want to do, that took this to being an alkyne, okay? And then what we needed to do from there is what we could have done is if we step this back one more time, we could have made this into, wait, why am I drawing a blank? Oh, okay, yep. Bromine, and this, what could have made this happen was NaNH2, and the way we could have made this happen would be Br2 and CCl4, right? So to put this all together, what you could have done, Br2, CCl4, that shoves bromine across your double bond. Then you just need to do a double elimination. You could use sodamide, NaNH2. That gets you your alkyne. You can hydrate that alkyne, forming on the more substituted carbon, right? Not with the boron reaction, with the mercuric sulfate reaction. Then you could throw in your ethyl Grignard. And last but not least, I'll write this in black to make sure it stands out, then we would need D3O+, okay? Now, again, I wanted to do this in the spirit of alkynes. However, if you did this a different way and you got a shorter path, which is always better, the way you could do that actually is, and it's very similar, instead of doing this right here, and of course I'm going to forget the reagents, but what you could have done was put in your mercuric acetate. I feel like that's a 2 there. Don't hate me, I kind of forget this as of right now. And I believe you need 8 water. There's, you know, doing the Markovnikov addition of water with no rearrangements at this position, that would give you this. And then you could just oxidize that with PCC and then do the rest. But again, like I said, I wanted to keep this in the spirit of alkynes, multiple ways of doing this. So if you're like, why didn't Joe put this on the solutions? Don't worry, it is a solution. I was just trying to keep it in the context of alkynes. Okay, 2 more, then the last problem. Let's finish the video. Okay, gang, to round out problem 2, we have 2 more, so let's go. So if we take a look here, right? First problem, we're just going to predict the product. Second part, we're filling the reagents. So in looking at the top, we have this aldehyde off of benzene, kind of off of benzene ring. So I hope you can see in the first step, we have this lovely alkyne nucleophile. We're just going to come in and attack, boot up electrons, right? And we, right, so in first step, you can see 1, 2 carbons, O-, and then from there we also have the, you know, the alkyne come in. So I hope what you're seeing also, and I'm going to go ahead and smush 1 and 2 together. I'm going to include the workup. So what I hope you're seeing in the benefit of doing problems stepwise like this is we did what was once not a stereocenter is now a stereocenter, right? Because we had no, or it's now a stereocenter because we're attached to 4 different things. Previously we also, you know, were trigonal planar, so we have no preference to attack on top or on bottom. So I'm going to carry through this as a wedge, but I will make a little note that this will most likely be racemic unless something changes along the way. Alright, so moving on to 3 and 4. Okay, so this is interesting, and I like this problem because it was almost simple, but sometimes I feel like this kind of stuff can trip students up. So, we have excess LDA. So basically what I was trying to aim with this problem is everything that can get deprotonated that's more acidic than usual is going to get deprotonated. What that means is this hydrogen and this hydrogen are going to get deprotonated. So, in step 3, we have an O-, and we have this alkyne right there. Now, I wanted to toss in a bunch of D3O+, and what that is aiming to do is just reprotonating. However, it's just kind of swapping in deuterium. So actually, for 4, and what is our final answer, is OD, and a deuterium there as well, plus an enantiomer from the alkyne nucleophile attack. But gang, I just wanted to kind of illustrate that, you know, just hammer home the whole, there are acidic protons around, you know, from the alcohol and the alkynes, the terminal alkynes that we've been working with and turning into nucleophiles. So I just wanted to deprotonate them, swap in some deuteriums to then, you know, of course, bring deuterium back into your life because we can never have too much. So that was what I was envisioning for this problem. Okay, so now down to here. So this is another longer kind of fill in the reagent section. So what I hope what you're seeing is we have 5 carbons. So what I hope what you're seeing is, okay, yeah, 1, 2, 3, 4, 5, and then this piece right here. So this is kind of the new kid on the block. This kind of looks like what we're working with over here, right? You can see the fork right here, the kind of isopropylish behavior, and then this methyl group, which is now a dash, and plus an enantiomer. So maybe, right, we do see we have an OH, so maybe we had this alkyne nucleophile come in and attack a carbonyl, which would explain how we got the racemic mixture. Okay, so what I think I'm going to start off with that. If we step this back, 1, 2, 3, 4. Yeah, so what I'm going to do is have, so you can see no chemistry happened here, but chemistry happened at this position right here. I'm going to say that was my carbonyl, okay? And what I'm going to say is I must have tossed in this alkyne nucleophile right here. That propyne right there attacking from the terminal position, right? So that must have been a first step. And then a second step was just H3O plus, nothing fancy here. Yep, no deuterium, I promise. So that explains how we got the product. Now we just need to get from here to there, right? So how do we get carbonyls? And again, yeah, I know we're doing alkynes, whatever, but you'd see that the way this is going to go, we're not going to get this carbonyl from an alkyne intermediate. I'm going to say we treated this with PCC, and we had this alcohol right there. Then what I'm going to say is that maybe we got this alcohol from a double bond, very similar to the one we're starting with, but not the same. And the way we could have gotten that, right, this is on the lesser substituted carbon of these two, so we could have done an anti-Markovnikov addition of water, hydroboration, right, boron, and then hydrogen peroxide and hydroxide. So in doing this, right, now we kind of need to do a double bond migration, if you will, right? So how did we get that to happen? So I think what we may have done here, and I'm going to start working from the front, is maybe we treated this with HBr, right, which would put a bromine on this carbon right here. Okay? Then from here to here, how we can connect the dots is do E2. And this would be our more substituted double bond. So I could even just toss in, what base did I use? Yep. So this is tertiary, so there's 0% chance of SN2. So if I threw in NaNH2 and some type of aprotic solvent like DMF, I'm absolutely only going to get elimination right here. Once we get that double bond, then I can put my OH on the lesser substituted carbon with hydroboration, right? That then gives me the alcohol I need in this position. I can oxidize it up to the ketone, the carbonyl I need, to then attack with the alkyne nucleophile to then get my product. So to put this all together, right, how does this look over the arrow? The first step is HBr. The second step is the NaNH2 and DMF. You know, you can include it, you can not include it, you can include a different solvent like DMSO or acetone, up to you. Then we need, whoops, this is step 3. Then we need, you know, your BH3, and then we need the H2O2 OH minus. Then we need the lovely PCC, and I'm running out of space, so I'm going to go ahead and erase this. Then I know it's a long one. Then bring in your propyne nucleophile. And last but not least, bring in your workup. So again, I designed these to be kind of a little over the top. So if you thought they were kind of over the top, then you're right. That was the whole point. So we're finally done with page 2, on to the tautomerization part of this worksheet and the end of the video. Okay gang, to finish off the worksheet, to cool off from all those complete reaction problems, let's do a little tautomerization. Why not, right? Okay, so if we take a look here, this is the equilibrium that has been provided for you. And in A, we're going to show the enol going to the ketone, and in B, we're going to show the ketone going to the enol. Let me just double check that's, because I'm doing 2 pages. Yep, sure enough. Okay, so in A, we're going from the enol to the ketone. So remember, it's all about making this look more like that. So if we go ahead and I'll redraw our enol. In the first step, remember, we have hydronium all over the place in solution, right? It could be hydronium, it could be acid, right? Like H2SO4, whatever, non-nucleophilic acid, something that's not going to participate, just going to give you H+, and then just wait. So what's going to happen here? We have a lot of electron density in the double bond. So this carbon right here will take these electrons, it will grab H+, we will dump the electrons onto the oxygen there. So in doing that, it's this carbon that is going to lose electrons, and we can counteract that. And again, you can do these in separate steps. I like to do them all in one step. What we can do is we can swing the electrons from the oxygen to reform a double bond right here, just so that this carbon doesn't lose any electrons. Or if you like to think about it like this, you can swing the electrons down from the oxygen. What that does is this carbon will break the octet rule if this bond doesn't go anywhere. So then this carbon can take them and pick up H+. Either way, whichever way you like to think about it. And really, these should be equilibrium arrows, because these go back and forth all the time. Well, I guess if we're going from this way to this way, I'm going to show you this way. Sure. Whatever. Should matter. Doesn't really matter. So in drawing this, right, now we have a double bond right here. Oxygen only has 1 lone pair, so now it has a plus formal charge because we're sharing one of its lone pairs that it used to control outright. And this hydrogen, just to show you, this hydrogen now exists right here. So to finish this out, the water we produced from here, or whatever conjugate base of the acid you're working with, it will help you clean up. It will do some cleanup. It will pick up H+, dump electrons onto oxygen, and this worked out because this is acid or base catalyzed. So if you produce the thing you were working with at the beginning, right, we have H0+ at the beginning, we have H3O+ at the end. That means, usually, not always, but you did it right. Okay, so now, down here, we will go from the ketone to the enol form, okay? So it's like everything we just did in reverse. I'm going to bring in my hydronium to start. The electronegative oxygen will love that. It will pick up the proton, the additional proton on, hydronium. Once we've protonated that oxygen, it now has a positive charge. We have water left over, and very similarly, in a very E2 fashion, very similar to this step up here, the reverse, I'm going to have water pick this off to free up these electrons. Once they are free, they will swing down to form a double bond. And if we do nothing, we're in trouble, because this carbon will break the octet rule with 1, 2, 3, 4, and a 5th bond. So we can't have that happen. The way we can get around that is we can dump electrons up here on oxygen. Oxygen, being the very electronegative atom that it is totally cool with that. Alleviates the positive charge it also has. So that's how we get the alkene character. That's how we get the OH, the oxygen, without the positive formal charge. And that's how we tautomerize. Okay, gang, I hope you found the answers you were looking for if you were coming here seeking alkyne explanations. I just want to say you're getting close to the end of OCHEM 1. You're so close. Keep grinding. I know your final's probably very soon in the not so far in the distance, but you're killing it. Good job. If you're watching this video, that means you financially supported jOeCHEM, and I can't thank you enough for that. I'm so glad you're choosing this is your outlet for organic chemistry knowledge. I hope you're having fun using it, as much fun as you can doing organic chemistry. I'm so glad you're using it right now. I hope you're using it in the future and to the the end, the climax of your organic career. But if anything, I'll see you all in the next video.